Regardless as to what the distant future holds, a global capsule pipeline transportation network is a viable, technically feasible, and highly realistic pipe dream of the present day. Arguably, the ideal method of transporting passengers and freight would be teleportation, which is currently at the experimental stage, with some success. However, the best we can strive for today is an infrastructure-dependent capsule-based system. Quite simply, passengers or freight are situated within a capsule, which is propelled through a pipeline evacuated of air on a guideway facilitating magnetic levitation and linear propulsion. This eliminates rolling resistance and reduces air resistance to a near negligible value, resulting in a very high speed and energy efficient system. Just such a system, called evacuated tube transport, has been proposed and will be discussed later. This technology has a clear foundation in the early 19th century, when it was initially utilized in the form of pneumatic capsule pipeline based on a proposal by George Medhurst published in 1810. The first practical and widespread implementation commenced operation in 1853. It was some 220 yards in length and linked the London Stock Exchange with the central station of the Electric and International Telegraph Company. By 1909 it had grown to some 40 miles of 3-inch diameter lead pipes running 30 centimetres under 50 London streets, powered by 4 steam engines. A capsule could carry up to 75 messages at a time, and by 1874 the network was conveying some 4.5 million messages annually. The popularity of pneumatic capsule pipelines grew. Networks of considerable size were constructed in many cities: Berlin, Paris, Vienna and Prague in the 19th century, and Munich in 1922, to name a few. The image depicts the Paris network, Les Pneumatiques. It was the largest such system, consisting from 1934 of some 467 kilometres of pipes. It was taken out of operation in 1984 due to advancements in electronic communications. Following on the success of the London system, in February 1863 a pneumatic, or atmospheric, railway entered service consisting of 2-foot 6-inch diameter pipes. It was primarily used to convey mail for the post office and connected the North-Western District Post Office at Eversholt with Euston Station. The system was declared the solution to London's street congestion, but due to poor reliability and maintenance costs, it was closed shortly after the turn of the 20th century. Similar systems became popular in America in the latter 19th century. Eventually, most post offices in New York City were connected to an 8-inch diameter system and equipped with a sending tube and pair of receiving tubes. Pneumatic capsule pipelines were not popular with all, however. Their commercial success in America posed a direct threat to the courier industry, which saw a decline in income as a result. Messenger boys would sometimes drop chewing gum, rubber bands and erasers into pipeline inlets to sabotage the system. One further notable system is the Post Office Railway of London, more commonly known as Mail Rail. This operated between 1928 and 2003. Although not a capsule pipeline system, a study of it can give insights to the benefits of an operational freight pipeline concept. Constructed to relieve London of some of its traffic congestion, Mail Rail was responsible for the removal of some 25% of London's mail vans from the city streets, with immediate effect upon commencement of operations. Its 34 trains conveyed some 12 million postal items across London daily. A single train could complete a circuit of the system in less than half an hour, including stops, some 3 to 4 times faster than a surface delivery van. This brings us to the present day. Current capsule pipeline applications consist primarily of 2 types: small bore pneumo-conveyors used by hospitals, banks, retail, etc., and larger bore systems used primarily for conveying ore, coal, sand, and so on. Capsule liner and magpipe are 2 examples of the latter type. Magpipe was developed to reduce the environmental impact of conveying ore for the Florida phosphate industry. It is a pneumatic system powered by linear synchronous motors in a pipeline with non-continuous motor windings. Each capsule contains an assembly of Hulbuck-arrayed permanent magnets and propels other capsules pneumatically as it passes over a winding. Peak velocity is 18 meters per second with a maximum payload 270 kilograms. This is an image of an automated rail mail delivery system I produced for Midas Station, which it was suggested to me I title Farewell Postie. Needless to say, Royal Mail were not very keen to help me with it. The concept I developed consisted of a 1 meter diameter main pipeline forming a closed circuit through which a 2 meter long capsule with a blockage ratio of 0.518 would traverse at a maximum velocity of 20 miles per hour, fully laden. The capsule would autonomously deliver mail by depositing it into a building-specific lateral pipe, as illustrated. The capsule is propelled by 2 linear induction motors, of which a pipe-mounted reaction rail forms the secondary. It receives electricity contactlessly via inductive energy transfer. Fully laden, 200 kilos, its power requirement in a straight and level pipe at 20 miles per hour is 848 watts. It is more than twice as efficient as a conveyor per unit mass of cargo than a typical light goods vehicle, and has a cargo volume capacity some 20 times that of a typical Royal Mail delivery pouch. Cargo Cap is a Germany-based system at an advanced stage of development. It is designed to conform with current freight convention and can accommodate 2 Euro pallets, each with a maximum payload of 1500 kilograms. Capsules are fully autonomous, electrically powered via inductive energy transfer, are driven by wheels connected to onboard motors, and run on tracks within a pipeline. Capsules are capable of a constant 36 miles per hour. Energy efficiency of the system is improved when they form a non-contact train with regulated spacing, creating an aerodynamic advantage. This brings us back to evacuated tube transport, ETT. It is the most promising system proposed and offers a wealth of advantages that have the potential to radically change life on this planet for the better. It is a system capable of transporting freight and passengers at speeds in excess of 4,000 miles per hour for international and cross-country journeys, and around 400 miles per hour for local trips. Acceleration is limited to 1g, thus a capsule requires some 166 kilometers to reach maximum velocity of 6,500 kilometers per hour, or 4,062.5 miles per hour, and does so in 184 seconds. Its minimum radius of curvature at that velocity is 332 kilometers. At 400 miles per hour, it is 3.3 kilometers. The mass of a capsule is 183 kilograms, and it has a 6-passenger capacity, or 367 kilograms of cargo. It is 4.95 meters in length and 1.3 meters in diameter, a size that would displace over 90% of present global transportation of people and goods. Once a capsule has been accelerated to speed by a linear motor, power is cut and it is left to coast in a near zero friction environment before decelerating when approaching its destination. At this point, the linear motor inverts to become a generator to reclaim some 90% of energy put into the capsule by means of electrodynamic braking. This greatly increases efficiency. In fact, ET3, the company behind the system, claims efficiency will be some 50 times greater than the most efficient electric cars or trains. Aided by its automated passive switching system at around 370 miles per hour, the system will exceed the capacity of a 40-lane motorway by having a design capability of 10 capsules per second, or 216,000 passengers per hour. At maximum velocity, the system has a capacity of 2.6 million passengers per hour, or 173 kilotons of freight. High-speed rail 2 will have a capacity of just 18,000 passengers per hour and zero freight. HS2 will also be much slower, with a top speed of 250 miles per hour. ETT requires very little maintenance, unlike modern rail, which is maintenance intensive. Further, ETT requires 1/20th the material to construct its guideways, consisting of two pipes, outbound and inbound, than is needed for conventional rail infrastructure. Due to its inherent material efficiency and automated production techniques, its monetary cost is 1/10 that of high-speed rail and a quarter the cost of building motorways. As it operates within a vacuum, the system is inherently silent, thus eliminating the problem of acoustic disturbance. The pipeline itself can be subterranean or mounted on stanchions, some 64 per mile. This would facilitate construction without the need to blight any vista or cause anyone to lose a home by compulsory purchase order. The system could be constructed below ground level using the pipe jacking method, or on the surface, only affecting current land use as electricity pylons or wind turbines currently do. This enables a very fast construction time, quite unlike the 20 years HS2 will require. Due to its low impact nature, ETT can be implemented without harming ecology or the environment, quite unlike HS2, which could be described as a destructive exercise in environmental vandalism. Compared with ETT, HS2 is as obsolete as it is inefficient and wasteful. It is overhyped and overglorified, restyled Victorian technology that should be consigned to history textbooks and museum exhibits, not have the countryside ripped apart and the biosphere further degraded in its implementation. Its disbenefits outweigh its benefits by a very large margin. It is not fundamentally different to the backwards rail system already in operation. It will be vulnerable to weather, noisy, an eyesore, a waste of resources, inefficient, dangerous, and a further ecological assault. It is clearly further evidence of the corruption and ineptitude of policymakers, people who have no place occupying positions of power. Compared with all current major forms of transportation, capsule pipeline is clearly the better option, with multifarious respects. The World Health Organization reports some 1.3 million human road fatalities and 50 million injuries globally per year. In the UK, some 5 people per day are killed on the roads. Transferring both passenger and freight from road to pipeline would put an end to such insanity. Capsule pipeline transportation is inherently safer due to its automation and protection of the enclosed environment afforded by pipes. There would be no one-unders with such a system, no risk of falling out of the sky as there is with air transport, and significantly reduced risk of drowning as there is with sea travel. Furthermore, with close monitoring of the pipeline structure, real-time predictive analysis of the surrounding environment, and multiple redundancy of control and other systems, the likelihood of calamity is all but eliminated. Replacing internal combustion engine powered transportation with electrically powered capsule pipelines would quickly eliminate disease associated with diesel emissions, which currently affects millions of people. It would clean up the air we breathe. Unlike cars, trucks and buses, capsule pipelines do not produce or spread deadly toxic pollution. The technology runs purely on electricity, which can be produced entirely from solar energy, a feasible idea when the relatively small amount of energy required to operate a capsule pipeline system is considered. Capsule pipelines would facilitate the removal of roadways which currently serve as barriers to wildlife. Further, road traffic causes countless wildlife fatalities each year, such that Foreman and Alexander in 1998 described the problem as the sleeping giant of conservation ecology. The image shows a rare animal bridge, but the real solution is a new mode of transport. A move to capsule pipelines would drastically reduce the pollution associated with automobile manufacture, oil spills, and prevent the removal of entire mountains for construction aggregate. Road freight crime, currently costing the UK some £250 million annually, would all but end. It would be hard to steal goods from a 1,000 miles per hour capsule inside a pipeline. Between 6 out of 10 to a more conservative estimation of 1 in 9 small package home deliveries fail, associated with both monetary and environmental costs. Automated direct home delivery, or to a nearby delivery receptacle, would end this problem. It would also significantly reduce warehousing requirements. Deliveries of goods would be prompt. Imagine ordering an item from America and receiving it within an hour. Having my fruits and vegetables delivered by pipeline would certainly make my life easier. Transportation would be reliable and unaffected by meteorological conditions. The internal pipeline environment would be invulnerable to snow and hurricanes. Consider a land unmolested and free of roadways and railway infrastructure, free from the constant and almost omnipresent noise of these things. A land not wasted but intelligently utilized and preserved for fauna and flora, ourselves included. This is the world we could have. How Jago and Rowe in '98 aptly expressed: roads are not efficient modes of transport. The space utilization of the actual item being transported to the space required by the transport operation itself is ridiculous. Power efficiency is appalling. The social disbenefits take some beating. The subsidy required for maintenance alone is huge. And why, in this age of technology, are people still having to undergo the stress of manual driving? Depressingly, some 15 years later, their comments are just as relevant today, if not more so. Capsule pipeline technology seems a rational single solution to a great many problems, so why is it not widespread today? It could be due to poor awareness, intermodal compatibility problems with existing infrastructure, or issues concerning the associated radical cultural and technological shift. The government does acknowledge some of its benefits, albeit in a few paragraphs buried in the appendices of a Commons Transport Committee report. Perhaps the real reason might be revealed when examining some of the potential effects of its widespread implementation. It would decimate the car, rail, ship and aviation industries. It would damage the pharmaceutical industry and close to wipe out the oil industry. It would also harm the banking, insurance and other financial industries. This might be why, but wouldn't our lives be so much better if this were to happen? Widespread implementation of the technology would take us a major step closer to ending the monetary system. A system based on belief, because that is all money is. It would help facilitate a new paradigm based purely on the resources available to us and human capacity for science and technology, an overdue system called the resource-based economy. There is no technical reason preventing a capsule pipeline system connecting every home as water, gas and sewage pipes currently do. It is lack of political will that curtails the technology. The contemptible and inexcusable withholding of this overdue technology seems due to continued efforts of policymakers to maintain the status quo. The idea of receiving goods from thousands of miles away within an hour of ordering, and the ability to travel hundreds of miles within a few minutes, are attractive notions and inspire imagination. However, these advantages are mere byproducts of a transport solution that would save countless lives, prevent massive destruction of wildland, bring a close to major global sources of pollution, and significantly improve the living quality of entire populations. I will end with a quote attributed to Albert Einstein. "We can't solve the problems of the world from the level of thinking we were at when we created them."